So here we go. Here's a piece of yard gravel kind. I think this is actually from the Gila River out by Safford. Um, and it's not a fossil. It's silicon carbide, and they form in tetrahedrons, and that's kind of what this is—a tetrahedron. Four triangular faces. It's been in the river, so it's been, tumbled with other bits and pieces of silicon carbide and diamond and the sand. And so, they get a little bit smoothed off and rounded over long periods of time. It's 10 on the Mohs scale of hardness, like a diamond, right? This is as hard as a diamond. So this was not something that happened in a couple of weeks, the rounding. And it looks like it got hot. Okay? And so if a stone falls from through the atmosphere, they fall heavy side down. And this would be the point, and all of the hot air is going in here and passing by, and that's how it flew down. I worked on it with my felt buff, so I didn't do anything other than just kind of clean the stuff off, and there's some goopy stuff in there, and it'll go away when I wash it. But otherwise, this is the way it was found on the ground, and my backyard actually has a lot of this kind of stuff. Because when the KT extinction event happened, the ship hit in New Mexico, and it literally cracked the planet. But the impact knocked up other things. There was like a fusion event because it was traveling at such great velocity. And it blew rocks, literally rocks like this, straight up into the air, up into outer space. But they're not traveling at 17,000 kilometers an hour to get out there. They're losing velocity all the way up, right? They're going up and going up and slowing down and slowing down and slowing down and slowing down. And eventually they reach a point where there's zero velocity going up, and then of course they come right straight back down, and they come down heavy side down, and you can see even the curve. This ablates away, the surface of the rock ablates away to try to cool the rock from that tremendous heat of moving through atmosphere at about from zero velocity. It starts falling towards the center of mass at 9.2 meters per second squared, and that's not it's per second squared. So it's each second gets a square. Okay? So the first second, it goes from 0 to 9.2 meters. Second, it squares that. The third second, it squares that. And that's why meteorites look like they're burning up, right? You're seeing the rock actually ablating away. And silicon carbide melts at 3,800 degrees, so not a lot of it melted, just a little bit of it. And what happens is there's metals in the planes of cleavage, and they're attracted to the heat, and that's what you see here. You see the metal across where the heat happened, because it got pulled through those planes of cleavage towards the place where it's hottest. So it's traveling that way and falling really, 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 really fast. Um, and so the ones that go up and come back down, are kind of rare, right? Because it's really hard to get things out that far enough to ablate when they fall back down. You try throwing a rock, see how far you get, right? And they don't go very far. It takes a tremendous amount of energy to put something straight up out of the Earth's gravity well into the even low Earth orbit, right? The low Earth orbit is between maybe 500 and 2,000 kilometers out. And generally, we orbit things about 2,000 kilometers, and they're traveling at 17,000 kilometers an hour to stay out there, right? It's like swinging a bucket around your head or something, and you can keep the water in it as long as you keep the bucket moving fast enough. And it's kind of the same idea. So you got to move really fast to stay out there. Otherwise, if you slow down, you fall and you burn up, right? Because I mean, like if I sent this metal out there, it would melt my platinum even. The platinum would probably make it, but none of the rest of it, the gold, would make it. But the palladium would ablate away. The gold is tied together with the platinum in double covalent bonds if it formed inside the Earth. And it doesn't melt worth a darn. Silicon carbide's about 4 times harder to melt because it's way up there at about 3,500 degrees. And it's got this metal in it from the AUPT as it passes through. And they're inside the planes of cleavage. And as it's falling, those metals are what's ablating away. And it's pulling the heat out of the rock and evaporating the heat off, just like water evaporating off of a boiling pan. So there's a little meteorite of silicon carbide. It's light, right? Carbon and silicon carbide don't weigh hardly anything. This is lighter than aluminum. Stronger than steel times 10 bazillion, because it's as hard as a diamond and it has double covalent bonds. It's not going to come apart. And we can machine this and make parts and pieces for machines just like you can with aluminum or steel. You can cut it in thin little slices and use the metal in those planes of cleavage to print printed circuits. With a laser, just draw pictures of printed circuits, and there you have it. because it's a semiconductor. It's silicon and carbon, both of which are semiconductors. But the joining of the two with those double covalent bonds is magnetic. Okay, and one's got more proton-electron pairs than the other one. And so they line up in north-south arrangements. But they're all going in every which direction, kind of in layers, right? Because it's a crystal. These are planes of cleavage. This didn't happen over millions of years. It happened in a matter of seconds, or hours or something, as the molten rock was cooling, right? And it holds a temperature for a long time, not because there's a flame or something under there, but because of the radioactivity in the molten rock. That's what makes it molten. It's the radioactivity that makes it molten. So that's this stuff floats in molten rock, and as the molten rock's moving up towards the surface, it's just floating there like this. But it was when it formed, it had sharp sides and stuff like a crystal usually does, and it's a tetrahedron because it's silicon carbide. And this is one of about half of the normal kind, but a tetrahedron is the simplest of the platonic solids, and it is a cubic crystal habit because it has 3 equal axes. 1, 2, 3. Yes, I certainly am. Thank you, sweetheart.